Welcome to the Daily History Chronicle. Each day, we travel back to discover a pivotal moment that changed the world. These aren't just dates and facts. They're stories of courage, conflict, innovation, and consequence that still echo through our lives today. Are you ready to explore? Let's see what happened on this day in history.
Good morning, I'm Richard Backus, publisher of University Teaching Edition, and every day I get to share a piece of history that I think you'll find as fascinating as I do. On January 6, 1912, a 31-year-old German meteorologist named Alfred Wegener stood before the Geological Association at the Senckenberg Museum in Frankfurt and proposed something radical. The continents weren't fixed in place. They had once been joined together in a single, massive landmass, a supercontinent he would later call Pangaea, and over millions of years they had drifted apart. Africa and South America fit together like puzzle pieces because they were once connected. The matching fossils, the identical rock formations on opposite sides of the Atlantic, these weren't coincidences. They were evidence of a fundamental truth about how our planet works. The geological establishment was not impressed. Many dismissed Wegener as a crank. Some called his theory delirious ravings and diagnosed him with moving crust disease and wandering pole plague. For decades, geologists would warn young scientists that even showing interest in continental drift would doom their careers. Wegener died in 1930 on an expedition to Greenland, his theory still rejected by mainstream science. And here's what fascinates me about this moment. Wegener was right. The continents had drifted. The evidence he'd gathered was essentially correct. But his explanation for how drift happened was utterly wrong. The scientific establishment rejected his theory, and they had good reasons for doing so. Understanding what happened on January 6th requires holding multiple truths. Wegener's observations were brilliant. His proposed mechanism was impossible. The scientific community's skepticism was justified. Their complete dismissal of his evidence was wrong. It would take 50 years and entirely new technologies to prove Wegener essentially correct, while also proving him fundamentally mistaken about the details. All these things are true. All these things matter. Picture this. It's late 1910, and Alfred Wegener is recovering from illness in a hospital. To pass the time, he's browsing through scientific journals. He comes across a paper listing identical fossils found on opposite sides of the Atlantic Ocean in South America and Africa. Fossils of plants that couldn't possibly have crossed an ocean. Fossils of land animals that couldn't swim thousands of miles. The prevailing explanation? There had once been massive land bridges connecting the continents, which had since sunk beneath the ocean. To Wegener, this made no sense. How could continent-sized land masses just sink? He'd been trained as a meteorologist and astronomer, not a geologist, so maybe he looked at geological puzzles with fresh eyes. He remembered something he'd noticed years earlier, something so obvious that cartographers had spotted it in the 1500s. If you look at a map, South America and Africa fit together like pieces of a jigsaw puzzle. The bulge of Brazil nestles into the indent of West Africa. It's not approximate, it's precise. What if, Wegener thought, they fit together because they had once been together? Over the next year, Wegener threw himself into research. He examined geological formations, specific types of rock appearing on both sides of the Atlantic. He studied glacial deposits that only made sense if continents had once been arranged differently. He cataloged fossils, systematic patterns of identical species on continents now separated by thousands of miles of ocean. One example particularly struck him: a small reptile called Mesosaurus, found in both Brazil and South Africa. Mesosaurus was a freshwater creature. It couldn't have crossed the salt ocean, yet there it was in rocks of identical age on both continents. The evidence kept piling up. Mountain ranges in Scotland matched those in the Appalachian Mountains of North America. Ancient glacial patterns made no sense in the continent's current positions, but made perfect sense if you slid them together. Coal deposits suggest that tropical forests once existed near what is now the Arctic Circle. By January 1912, Wegener was convinced the continents had moved. On January 6th, he presented his hypothesis to the Geological Association in Frankfurt. His presentation was bold, comprehensive, and revolutionary. The meeting notes recorded that there was no discussion due to the advanced hour, the same polite dismissal that greeted Darwin's theory of evolution decades earlier. But here's where Wegener's theory hit a wall. He couldn't explain how continents moved. He proposed two mechanisms. First, he suggested the centrifugal force from Earth's rotation might push continents toward the equator. Second, he theorized that the astronomical troops, tidal effects from the sun and moon, might drag continents through the ocean floor. Geologists immediately recognized these explanations as impossible. The forces Wegener proposed were far too weak to move continent-sized land masses. As one critic put it, his mechanisms would be like trying to move an elephant by blowing on it. The oceanic crust was too strong for continents to simply plow through it, as ships do through water. Wegener himself knew his mechanisms were weak. In his writings, he acknowledged this gap. He hoped that someday, someone, he called it the Newton of drift theory, would discover the actual mechanism. But until then, he believed the evidence was too compelling to ignore, even though the explanation remained incomplete. The scientific establishment disagreed. Their position was clear. Extraordinary claims require extraordinary evidence. And part of exceptional evidence is a plausible mechanism. You can't just show that something appears to have happened. You need to explain how it could happen. The criticism wasn't just scientific, it became personal. German geologists mocked Wegener's delirious ravings. British scientists ridiculed him for being a meteorologist, daring to tell geologists how the Earth worked. The American Association of Petroleum Geologists organized an entire symposium specifically to refute continental drift. One geologist wrote that Wegener's theory plays a game in which there are few restrictive rules and takes considerable liberties with our globe. There was also this uncomfortable truth. If we are to believe Wegener's hypothesis, one critic admitted, we must forget everything which has been learned in the last 70 years and start all over again. And there was the heart of the problem. Wegener wasn't just proposing a new idea. He was asking scientists to abandon the entire framework on which they built their careers. Wegener never backed down. He refined his arguments, addressed valid criticisms, and updated his timeline when geologists proved it was too short. But he never retracted his core claim. The continents had moved. He kept going back to Greenland, conducting meteorological research, studying glaciers, gathering more data. In November 1930, on his fourth expedition to Greenland, Wegener disappeared during a supply run across the ice cap. His body was recovered months later, buried carefully in the snow by his companion, who had then continued alone and also vanished. Wegener was 50 years old. His theory was still considered pseudoscience, and then, in the 1950s and 1960s, everything changed. New technologies allowed scientists to study the ocean floor. They discovered something Wegener had actually speculated about but never developed: mid-ocean ridges where new seafloor was continuously forming. They found that rock magnetism recorded in seafloor sediments showed the continents had indeed moved. They discovered that Earth's crust wasn't solid, but broken into massive plates that grind against each other. The mechanism Wegener couldn't find? It was convection currents in Earth's mantle, driven by heat from the planet's core. The continents weren't plowing through the ocean floor. They were riding on plates that were constantly being created at some boundaries and destroyed at others. By the mid-1960s, continental drift had become plate tectonics, the unifying theory of geology. Wegener had been right about the big picture while being wrong about almost every detail of how it worked. We're still living with the lessons of Wegener's story. How do you evaluate revolutionary ideas that challenge everything experts believe? On one hand, the scientific establishment's skepticism was warranted. Wegener couldn't explain the mechanism. His proposed forces were physically impossible. By the rigorous standards of science, his theory had a fatal flaw. But dismissing the theory entirely meant ignoring overwhelming observational evidence. The continents did fit together. The fossils were identical. The rock formations did match. These facts didn't stop being true just because Wegener couldn't explain why. This tension plays out today in countless scientific debates. When someone challenges scientific consensus, we face Wegener's dilemma. Do we demand a complete explanation before accepting any part of a revolutionary claim? Or do we take observational evidence seriously even when we can't explain the mechanism? Climate science faces this constantly. We observe rising temperatures, melting ice, and changing weather patterns. Critics sometimes argue that if scientists can't predict every detail perfectly, the whole theory must be wrong. But Wegener teaches us that you can be right about fundamental truth while being wrong about mechanisms. The story also reveals the danger of gatekeeping in science. Wegener was an outsider, a meteorologist working on geological problems. Many attacks on his theory focused not on the evidence, but on his credentials. He wasn't a real geologist. He was an interloper who didn't understand how things worked. But sometimes outsiders see patterns that insiders miss precisely because they're not invested in the current paradigm. Wegener looked at a map with fresh eyes and saw something obvious that geologists had trained themselves not to see. The lesson isn't that every outsider with a revolutionary theory is correct. Most aren't. The lesson is more subtle. Wegener's evidence was strong, but his mechanism was wrong. The scientific establishment was proper to demand a mechanism, but bad to dismiss the evidence entirely. Both sides had legitimate points. Both sides made mistakes. The resolution came not from one side winning an argument, but from new technology, revealing a truth neither side had imagined. The continents moved, but not the way Wegener thought. The Earth's crust was broken into plates, which geologists hadn't known. Everyone was partly right and partly wrong. This is how science actually works, not as a battle between right and wrong, but as a process of refining ideas, testing evidence, developing new tools, and gradually converging on the truth, even when nobody had the whole picture to start with. What troubles me most is how personal the attacks became. Calling someone's ideas delirious ravings or diagnosing them with plague isn't scientific criticism, it's mockery designed to silence. When scientists warn colleagues that showing interest in an idea will doom their careers, that's not skepticism, it's suppression. Wegener endured this for 18 years. He kept refining his theory, gathering evidence, and believing he was right, even when nearly everyone said he was wrong. That takes extraordinary conviction. But conviction alone doesn't make you correct. For every Wegener who's eventually vindicated, countless others we're just as convinced and just as wrong. So how do we tell the difference? We can't always, not in the moment. That's the uncomfortable truth. The scientific method helps over time, but in the moment, when paradigms are shifting, even experts can't reliably distinguish revolutionary truth from compelling error. I'm Richard Backus, and this is the Daily History Chronicle. Tomorrow, we'll explore another moment that shaped our world. Until then, think about this. When someone challenges scientific consensus with compelling evidence but no mechanism, how should we respond? When an outsider proposes something revolutionary, how do we balance openness to new ideas with healthy skepticism? And when we're certain we're right about something fundamental, how do we remain open to the possibility that we've missed something obvious? Because that's what Wegener teaches us. Not that consensus is always wrong, but that the most essential truths sometimes hide in plain sight, waiting for someone brave enough or naive enough to see what everyone else has trained themselves to ignore. Thank you for your time. If you enjoyed this episode, then please subscribe. If you really enjoyed it, then please tell a friend. I hope you will join me again tomorrow for more of our shared history.